Okay, we are starting 19.6, magnetic torque. And let's go to the next slide. Let's think about what happens when a loop of current is placed in a magnetic field. Consider the figure on the left, which shows a rectangular loop carrying current I in the presence of an external uniform magnetic field in the plane of the loop. The forces on the sides of length A are zero because these wires are parallel to the field. The magnitudes of the magnetic force on the sides of length B, given in the equation here, F equals F1 equals F2 equals BI little b, for B being the segment. The equation of F1, the force on the left side of the loop, is out of the screen, and F2, the force on the right side of the loop, is into the screen. Now let's look at the figure on the right where we can see the loop from the side. The forces are directed as shown. Let's assume the loop is pivoted so that it can rotate about a point O. You can see that these two factors produce a torque about O that rotates the loop clockwise. The magnitude of this torque, T max, is given in the equation. There it is. T max is given in the equation, where the moment arm about O is A over 2 for both forces. Because the area of the loop is A, the maximum torque can be expressed as shown. BI times the area. This result is valid only when the magnetic field is parallel to the plane of the loop, as in the figure to the right. Okay, so you end up getting a little rotation, and we'll see how that's used. Okay, if the field makes an angle theta with a line perpendicular to the plane of the loop, as in the figure here, the moment arm for each force is given by the expression shown, A2 over sine theta. If we follow a similar analysis to the previous slide, we will get this expression. The torque equals BIA sine theta, where B is the magnetic field, I is the current, A is the area, and sine theta is the angle shown. Now, notice that the theta is normal to the coil. So it's not the coil itself, it's the normal vector that is perpendicular to the coil. This result shows that the torque has the maximum value BIA when the field is parallel to the plane of the loop. That is, theta equals 90, and is 0 when the field is perpendicular to the plane of the loop. As you can see in the figure, the loop tends to rotate to smaller values of theta so that the normal to the plane of the loop rotates toward the direction of the magnetic field. Even though our analysis was for a rectangular loop, a more general derivation will show that our result applies regardless of the shape of the loop. Also, the torque on a coil with n turns is given here. So it's just tau is equal to BIAN sine theta, where n is the number of turns. Let's define the quantity IAN as mu. IAN, mu equals IAN, therefore the torque equals mu b sine theta. We can rewrite our torque equation. The quantity mu is the magnitude of the vector mu, called the magnetic moment of the coil. This vector always points perpendicular to the plane of the loops, to the loop or loops, and if the thumb of your right hand points in the direction of mu, your fingers point in the direction of the current. The angle theta in these equations lies between the directions of the magnetic moment and the magnetic field. Note that the torque is always perpendicular to both the magnetic moment and the magnetic field. It's hard to imagine life without electric motors. Motors are used in computer disk drives, CD players, DVD players, food processors, and blenders, car starters, furnaces, and air conditioners. The motors convert electrical energy to kinetic energy of rotation and consist of a rigid current carrying loop that rotates when placed in a magnetic field. As we've just seen, the torque on the loop in the figure rotates the loop to smaller values of theta until the torque becomes zero, where the magnetic field is perpendicular to the plane of the loop and theta equals zero. If the loop turns past this angle and the current remains in the direction shown, the torque reverses direction and turns the loop in the opposite direction, that is counterclockwise. In order to provide continuous rotation in one direction, the current in the loop must periodically reverse direction. In alternating current motors or AC motors, this reversal occurs naturally 120 times each second. In direct current motors, the reversal is accomplished mechanically with split ring contacts called commutators and brushes, as you can see in this figure. Although actual motors contain many current loops and commutators, for simplicity, our figure shows only a single loop and a single set of split ring contacts rigidly attached to and rotating with the loop. Electrical stationary contacts called brushes are maintained in electrical contact with the rotating split ring. These brushes are usually made of graphite because it is a good electrical conductor as well as a good lubricant. Just when the loop becomes perpendicular to the magnetic field and the torque becomes zero, inertia carries the loop forward in the clockwise direction, and the brushes cross the gaps in the ring, causing the loop current to reverse its direction. This reversal provides another pulse of torque in the clockwise direction for another 180 degrees. The current reverses and the process repeats itself. This figure shows a modern motor used to power a hybrid gas electric car. Okay, I'm going to also show you a Walter Fendt demonstration using that describes electric motors. And this ends the section on magnetic torques on a carrying current conductor. The next section is section 19.7, Ampere's law, but we will deviate a little bit and look at a Walter Fendt demonstration.